When we think about gravity, it seems pretty simple, right? What goes up must come down. It's a force, something that pulls you to the ground. That was Isaac Newton's big idea. And hey, it worked brilliantly for over 200 years. But then this patent clerk, Albert Einstein, comes along and asks a really wild question. What if gravity isn't a force at all? What if it's the actual shape of the universe? And let me tell you, that idea changed absolutely everything. So on one hand, you've got Newton's gravity. Think of it as this mysterious, invisible force that just zaps across empty space instantly. It's like a cosmic string pulling an apple down from a tree. But then, on the other hand, you've got Einstein. In his universe, there is no force, no string. Instead, things with mass and energy, like planets and stars, literally bend and curve the very fabric of space-time. And by space-time, I just mean the 3 dimensions of space and the 1 dimension of time all woven together into this single flexible sheet. So objects aren't being pulled, they're just following the curves. It's the path of least resistance through a warped reality. Now, to really get why Einstein felt the need to just completely rewrite physics, we have to go back to Newton. I mean, his laws describe this beautiful clockwork universe. They could predict the orbits of planets, the path of a cannonball. Everything seemed to fit perfectly. Almost perfectly. There was just one tiny little crack in this perfect machine. For centuries, Newton's idea was the only game in town. It was just a fact of life, a force that just is. And even Newton himself thought the idea of a force acting across a vacuum was kind of absurd, but the math worked so well that everybody just went with it. The universe was this fixed stage, and gravity was the invisible puppet master pulling all the strings. But there was a ghost in the machine. The planet Mercury, the one closest to the sun, just refused to follow Newton's rules perfectly. Its orbit wasn't a clean, repeating ellipse. It wobbled, or precessed, just a tiny bit more than Newton's laws could explain, even when you accounted for the pull of all the other planets. It was a real troublemaker. So just how small was this error? Only 43 arcseconds per century. Okay, to give you an idea of how small that is, an arcsecond is 1/3600th of a single degree. I mean, for you and me, that's a rounding error. It's nothing. But for astronomers, for them, it was a screaming siren that meant something was fundamentally wrong with how they saw the universe. And this just shows you how much faith everyone had in Newton's laws. The thinking was, well, the laws can't be wrong, so there must be something else out there we can't see. The leading theory? An undiscovered planet, somewhere between Mercury and the Sun, tugging on Mercury and causing that extra wobble. They even gave it a name, Vulcan. And for decades, you had this Vulcan mania, with astronomers claiming they'd spotted it. But of course, Vulcan wasn't there. So the solution to Mercury's weird wobble didn't come from finding a new planet. It came from a completely radical new idea about what space and time and gravity actually are. And Einstein's big breakthrough didn't start with a telescope. It started with a simple thought experiment. Okay, picture this. You're in an elevator with no windows. You feel yourself being pressed to the floor. Now the question is, are you sitting on a launch pad on Earth, feeling the pull of gravity? Or are you way out in deep space, and the elevator is just accelerating upwards? Einstein realized there's no experiment you could possibly do inside that box to tell the difference. This simple idea, that gravity and acceleration are basically the same thing, is the absolute cornerstone of his new theory. So if gravity and acceleration are the same, then falling isn't a force pulling you down at all. It's just you following the straightest possible path through a bent universe. Think about an astronaut in orbit. They're in free fall, right? They feel weightless because there's no force acting on them. The real force is the one you're feeling right now, the ground pushing up on your feet, stopping you from following that natural curved path through space-time. And this is the beautiful, elegant dance of general relativity. It's not a one-way street. The Earth's mass warps the space-time around it, and that warped space-time tells the moon how to orbit. They're locked in this dynamic, geometric relationship. So the key takeaway here is that gravity isn't a force, it's just a feature of the universe's geometry. All right, so if Einstein's right and we're all living on this flexible, four-dimensional cosmic fabric, the consequences should be pretty bizarre, right? Well, they are. His theory predicts that not only can space be bent, but time itself can be stretched and squeezed by gravity. Okay, here's another quick thought experiment. Imagine you drop a particle from the top of a tall tower. As it falls, it gains energy. Now, let's say you could convert all that energy into a photon, a particle of light, and shoot it back up to the top. Well, to avoid creating a perpetual motion machine, that photon has to arrive back at the top with the same energy it started with. That means it must lose energy climbing out of the gravitational field. And since a photon's energy is directly tied to its frequency, you can think of it as its internal clock. This means time itself must be ticking slower at the bottom of the tower than it is at the top. Wild, right? And this isn't just some theoretical curiosity. It is very real. This number, 38 microseconds, that's how much faster the clocks on GPS satellites run every single day compared to clocks down here on the surface of the Earth. They're in a weaker gravitational field, so for them, time literally moved faster. And why should you care about this? Because your phone's GPS absolutely relies on this. The whole system needs nanosecond timing to figure out where you are. Without constantly correcting for that 38 microsecond daily drift predicted by relativity, the entire GPS network would fail in minutes. Your location would be off by miles every single day. So yeah, every time you use Google Maps, you are personally proving Einstein right. So look, a beautiful theory is one thing, but science demands proof. Cold, hard evidence. And over the last century, the evidence for Einstein's radical vision of the universe has become pretty much overwhelming. Let's go back to our original mystery, that pesky wobble in Mercury's orbit. When Einstein plugged the numbers into his new equations, he wasn't trying to make it fit. He just calculated what the orbit should be in a universe where the sun's massive gravity is warping spacetime. And the result? It predicted that extra 43 arcsecond wobble perfectly. The phantom planet Vulcan, poof, vanished forever. But the next prediction was even more spectacular. The theory said that gravity should be able to bend light itself. So in 1919, an expedition led by Sir Arthur Eddington photographed the stars near the sun during a total solar eclipse. And they found that the starlight was, in fact, bent as it passed by the sun's enormous gravity, exactly by the amount Einstein had predicted. This discovery made him a global superstar overnight. Today, we see this effect, which is called gravitational lensing, everywhere we look in the cosmos. I mean, just look at this beautiful image. It's called an Einstein ring. The light from a really distant galaxy, which is directly behind that closer, massive one, is being bent and magnified into this stunning, nearly perfect halo. The galaxy in the front is acting like a giant cosmic magnifying glass, a direct visual confirmation of curved space-time. But maybe the most profound prediction of all was that space-time isn't just static and curved. It can ripple, it can jiggle. Huge cataclysmic events, like two black holes smashing into each other, should send out gravitational waves, actual vibrations in the geometry of the universe. This is LIGO, an incredible machine designed to detect those impossibly faint ripples. And in 2015, they did it. They succeeded. For the very first time, humanity detected a gravitational wave. The signal was this unmistakable chirp of two black holes spiraling into each other and merging into one. We didn't just have to see the evidence for Einstein's theory anymore. We could now actually listen to the soundtrack of the cosmos. We could hear the fabric of space-time itself ringing like a bell. And this brand new sense has revealed a universe of incredible violence and beauty. Every one of these events is a collision. Black holes merging, neutron stars crashing together. It's a map of a stellar graveyard that was totally invisible to us before. This is the universe that Einstein gave us, not some quiet clockwork machine, but a dynamic, ringing cosmic fabric. So we've journeyed from a simple force to the actual geometry of the universe itself. And it leaves us with this really tantalizing thought. Einstein showed us that gravity is basically an illusion, a property of a deeper reality. So what if the other forces are too? Could electromagnetism, or the nuclear forces, could they also just be shadows of a more complex geometry, maybe in dimensions that we just can't see yet?